Okay. So, on to Chapter 5, our next chapter. We're finally done with Chapter 4. Chapter 5 is all about gases. And we talked about gases here and there, but never to any great amount of detail. Here's where we learn all about gases in this chapter. First off, how do we measure gases? Turns out most of the measurements for gases we're already familiar with, but there's going to be a new one that we haven't seen yet. And that new measurement is pressure. You can certainly apply pressure to solids and liquids, but it doesn't really have a whole lot of effect on solids and liquids. Pressure, though, has a big impact on gases. So a brand new measurement for us. When we talk about the pressure of gases, what we most often experience in terms of gas pressure is atmospheric pressure. So let's look at that first. What is atmospheric gas pressure? Well, there's the Earth. And on top of the Earth, we have, let's see, who should be on top of the Earth here? How about Travis? Well, Travis on top of the Earth eating his hot dog. There. Now, as Travis or any of the rest of you stand here on the Earth's surface, you are experiencing atmospheric pressure because there is atmosphere above you. Quite a bit of it, in fact. There's a couple of miles of atmosphere. We don't normally think of atmosphere as having a lot of weight because it really doesn't have much weight. However, if you think of a couple of miles of atmosphere, that actually has a collective weight to it. And that's what we experience as atmospheric pressure. As you stand here on the Earth's surface, you have a couple of miles of atmosphere above you, and the weight of that atmosphere pushes down on you. So Travis here is experiencing atmospheric pressure pushing down on him, just the weight of the atmosphere above him. And it doesn't just push down on the top of his head, it pushes down on him from all sides. There. Yes?
What if you're inside?
What if you're inside?
Yeah, just
Can you escape air?
No.
No, you can't. So actually, even if you're inside here, the atmospheric pressure, the air is being pushed down and in and from all around. You're still getting surrounded with it. You can't normally escape the atmosphere. Sometimes, but not. Now looking at this, believe it or not, this drawing is slightly out of scale. Just a little bit. Turns out the atmosphere is not quite as big as I'm letting on here. This is kind of a scary thing. If this were an actual scale model of the planet Earth, the actual atmosphere would be this tiny, tiny thin line that you could barely see. We don't have a whole lot of atmosphere. A couple of miles of atmosphere sounds like a lot until you think of how big the Earth is. Our atmosphere is tiny. Very, very small. Could blow away in a second and we'd all suffocate. So bear that in mind. When you're nervously sitting up late at night, bear that in mind. The atmosphere would just blow away at any time, we'd all be dead. Okay, anyway, there we have our slightly out of scale picture here. Now, how do we measure atmospheric pressure? We experience atmospheric pressure all the time, but how can we measure it? In science, we measure atmospheric pressure using a device called a barometer. And here's how you construct a barometer, should you want to do so. And by the way, I recommend not constructing a barometer. It's not a good idea. And here's why. The main ingredient to making a barometer is a dish full of liquid mercury. That's not the healthiest kind of stuff to have sitting around. So you have your dish of liquid mercury. To construct the barometer, what you want to do is get yourself a very, very long, skinny test tube. What it really is a glass tube sealed off on one end, but it looks like a giant test tube. What we're going to do is we're going to fill this all the way up to the very top full of liquid mercury. We don't want any air in there at all, just pure liquid mercury. Then I'm going to stick my thumb right on the top of that. Then I'm going to flip this over, stick this under the surface of the liquid mercury, take my hand away, and presumably wash my hands. So now we've got this set up right here. Now remember, this tube here was completely filled with mercury. As it sits here in the dish, though, what will quickly happen is the mercury will not stay at the very top of the tube like this. It will start to drop down. And it will stop at a certain level. Now all this area here is still full of liquid mercury. But this part here no longer has any liquid mercury in it. What is there now?
Pressure.
Air. How did air get in there? Remember, this tube was completely filled with mercury, no air bubbles at all. I turned it over, let it go inside this dish of mercury. How did air get in there? Pressure. It is a vacuum. Chandler is right. So what we actually see in this empty area here is nothing. That is vacuum. There's nothing there at all. Now that being the case, why doesn't the mercury drop all the way down into the dish? What is holding this column of mercury in place?
Pressure.
Pressure. From what?
The atmosphere.
Yes. Now I was waiting for someone to say the vacuum is holding it up. Anyone thinking that? The vacuum is holding it up? You liars. Well, as it turns out here, vacuum is nothing, remember? Vacuum is complete absence of everything. So vacuum has no force at all. It's got nothing to it. So vacuum can't do anything. This is just pure nothingness. But this barometer is on the Earth's surface just like Travis's. So that means atmospheric pressure, which would be the weight of the atmosphere above this device, is pushing down on it. So as the atmospheric pressure pushes down on the surface of this mercury, that pressure pushes the mercury up into that glass tube and holds it in place. So this column of mercury is held in place by atmospheric pressure. But this column of mercury is not going to have a constant height to it. What do you think would happen if the atmospheric pressure increased? What do you think would happen if it was pressing down on the mercury harder? What would happen to the level of mercury in this tube here? It would rise. And conversely, let's say the atmospheric pressure went down and wasn't pushing on the mercury quite as hard, then this mercury level would decrease. So it turns out the height of mercury in this tube is directly proportional to atmospheric pressure. And under normal conditions, if we were to measure the distance from the surface of the mercury in the dish to the top of the mercury in the column, it would measure 760 millimeters. That's how high that column of mercury would be. Just to be specific here, we'll often add Hg there. Oh, man. Thank you. I'm allergic to mercury. There. So to be specific here, we'll say millimeters of mercury. Now this is what the atmospheric pressure is under normal conditions. Might be helpful to define what exactly normal atmospheric conditions are. First off, turns out I was lying before about my little model of the Earth over here. So it's not to scale. It's also not quite as round as I've depicted it either. You guys are aware that the Earth spins on its axis, right? That's why we have day and night. The Earth is spinning on its axis. Turns out if you have a globe spinning on its axis, what's going to happen is it's going to bulge out around the middle. That's a consequence of having a sphere spinning around on its axis. So our Earth is not going to quite look like this. Jump, Travis. Hold your breath, too.
Yeah, because the atmosphere is going to keep that out.
I'm exaggerating this a little bit. More than I wanted to. I'm exaggerating this a little bit here, but the idea again is that this sphere spinning on its axis here is going to be bulging out around the middle. And not only is the Earth itself going to be bulging out around the middle, but the atmosphere is also going to be bulging out around the middle. Like that. So it turns out, depending on exactly where you are on Earth, there is a different height of atmosphere above you. So let's say Anna is vacationing on the equator. I don't have a brown marker. You have to have green hair for now. There you go. So there's Anna vacationing on the equator. Now look at the height of the atmosphere above Anna versus the height of the atmosphere, I'm going to duck here.
There we go.
Now you can breathe. So notice there's a difference in height there of the atmosphere. So who is experiencing greater atmospheric pressure here? Travis or Anna? Anna. Fine, I'll exaggerate this a little bit more for your sake here. Maybe this will help. A little bit more bulging effect going on here. There. So let's try this again. Who has more atmosphere above their heads? Anna does. So that means that Anna is going to experience more atmospheric pressure than Travis is. And in fact, going from the equator up in latitude, the higher in latitude you get, the less atmosphere is above you and the less atmospheric pressure you have. The minimum would be at the North Pole here. And the same thing happens going south. So as you move south, the atmospheric pressure gets steadily less because you have less atmosphere above you, and it reaches a minimum at the South Pole. So normal atmospheric conditions, which would give us normal atmospheric pressure, normal only occurs at the equator. As you move away from the equator, either north or south, you have less atmosphere above you and therefore less atmospheric pressure. But there's more. The Earth is not a smooth surface. There's also mountains. Let's say Kelly here decides to climb Mount Everest. He's going to be perched precariously right on top here. They give you blue hair. Actually, that'll work.
Do they only have like, is that a ponytail? Or is one side of
You're
it?
criticizing my artistic ability?
I didn't know, like I was just wondering.
Yes, it's a ponytail.
Okay.
That'll be easier to draw, sure.
Double check it.
All right. Anyhow, if Kelly is up on top of Mount Everest, what kind of atmospheric pressure is she experiencing?
Not much.
Not that much. Because again, atmospheric pressure is the weight of the atmosphere above you. So if you're at a really high elevation, there's not a whole lot of atmosphere above you. Therefore, less atmospheric pressure. And not to be outdone here, Chandler, being far too bored in class, decides to go vacation in Death Valley over in California. So there's Chandler at the bottom of Death Valley, straddling precariously here. There we go. Now what kind of atmospheric pressure is Chandler going to be experiencing? A lot. Because not only does he have the atmosphere above the surface of the Earth, he has this extra atmosphere down here as well. So Chandler's experiencing extra high atmospheric pressure. So atmospheric pressure is not just a function of latitude, it's also a function of elevation. The higher your elevation, the lower the pressure, because the less atmosphere you have above you. And the lower your elevation, the higher the pressure, because you got more atmosphere above you.
Does that work into like with water pressure too? Like
I'll talk about that in a second. Yep. So anyway, back to normal. What would normal be? Well, we'll split the difference there and say at sea level. And we'll just recognize that as we go above sea level, the pressure will decrease. As we go below sea level, the pressure will increase. And Patrick, taking some advice from Chandler, decides he's going to go scuba diving in the Marianas Trench. Sound good? So, there we go. Now here's the deal. Patrick is here scuba diving. Marianas Trench is kind of deep. You gonna take any special precautions? You just put on your tank and dive down a few miles. You good with that?
Yeah.
Good for you, sure. So there's Patrick. Down there, my artistic abilities are disintegrating by the moment. So there's Patrick with a scuba tank there. Now what kind of atmospheric pressure is Patrick experiencing? Well, he's experiencing all the pressure of the actual atmosphere above the surface of the ocean pushing down, but he's got more than that. He not only has atmosphere above him, he has a couple of miles of salt water above him. Is salt water heavier than air?
Yeah.
Quite a bit, yes. So you are under extraordinary pressure down there. Way, way crazy pressure, like a couple of hundred atmospheres probably. You okay down there? No, you're not. Now, pressure only really impacts gases. It doesn't really impact solids or liquids too much. But Patrick has got some gas in him. What's the major source of gas in Patrick? Like location.
Lungs.
Yeah, lungs. So what's going to happen there is Patrick's lungs are going to be compressed down to pretty much nothing, and he won't be able to breathe. Your eyeballs also tend to have some gas in them too, so they'll be squished. It's gonna hurt.
What about his ears? Like I know when you.
Oh yeah, his ears will be the least of his problems.
Oh, okay.
They'll hurt a lot too, though. He won't feel that over the intense pain in his eyeballs and lungs. So. Yes, Thomas.
Did you see that Mythbusters when the scoop diver got pressed up into his helmet?
Oh, I actually think one of his sons showed me that.
And it's because they're in like his old suits where it was like they had to keep the pressure in the suit, but then the helmet was metal, and if there's lost pressure in the suit, they just their whole body was in their helmet. It was crazy.
Wow.
Interesting.
Another reason to not do that.
Another-
Yikes. There we go. So, back to normal. So we're seeing all these abnormal situations here. So normal, remember normal is 760 millimeters of mercury as measured on the barometer. Normal would be at the equator and at sea level. And we see how the different elevations and latitudes affect that. There is one final effect, though, to normal atmospheric pressure. And that would be the weather. Turns out the atmosphere is not a uniform thing. It varies. Occasionally you can have certain areas of the atmosphere that have a little bit more atmospheric pressure than other areas of the atmosphere. Now, if you ever watched the Weather Channel, you've seen this. It's kind of freaky, actually, kind of frightening. You ever see the Weather Center maps? They have these giant capital H's and giant capital L's floating overhead. If you look up carefully in the sky, you can see them. They're kind of floating overhead all over the place. What do you think that means? High and low. So again, the atmosphere is not constant. It can have temporary pockets that are a little higher in pressure than others, high and low systems. What we're talking about for normal weather here is the H's and L's are elsewhere. We don't have them anywhere above us right now, so we can relax. That's normal weather. So under these conditions right here, if these conditions are met, your barometer should read about 760. Now it turns out, this is kind of weird here, we've got a barometer in lab, by the way. Has there been an open dish of mercury in lab all this time? Yeah, there has been. Just don't breathe in lab and you'll be fine. So anyway, it's been there the whole time. As it turns out, this is kind of interesting here, our atmospheric pressure in Florida is typically right around 760. Which is kind of weird, because we're higher in latitude than the equator, so that should decrease our pressure. And we're also a little bit above sea level. So that should also decrease our pressure. As it turns out, we here in Florida have a hard time escaping those big capital H's. They're almost always overhead. So that exactly counteracts that effect, and we are almost always right around 760. Weird. Perfect indeed. So, normal atmospheric pressure is going to be defined as 760 millimeters of mercury height in a barometer. That's kind of a big, nasty unit there, millimeters of mercury. So we scientists have worked out a kind of a more concise way of expressing this. We call 760 millimeters of mercury 1 atmosphere, or in other words, 1 atmospheric pressure. That's way too many letters, so we commonly abbreviate that ATM. So a good abbreviation for atmosphere also helps remind us how little money we scientists have. There it is. So that is pressure, this brand new measurement we are going to use for gases. And as we've seen here, pressure is going to be ultimately measured in atmospheres. Now really it's measured in terms of millimeters of mercury, but can you convert millimeters of mercury to atmospheres? You sure can, because I just gave you a conversion factor right here. So using dimensional analysis, you can now convert millimeters of mercury to atmospheres, or back again as needed. So here is pressure. The other measurements we're going to use for gases are ones we're already familiar with. Our next one is going to be volume. We can measure the volume of a gas. What do you think would be a good unit for measuring volume? That'd be a unit, not a good one though. It'd be a nice easy one. For volume? Volume? Liters, there we go. Milliliters. There. So we will measure our volume in liters, just like we always have. Remember, everything else I'm going to talk about stuff we're already familiar with. Pressure was the only new one. On top of pressure and volume, we can also measure amount of gas present. Now we can technically measure grams here, but grams is a little bit vague. We've got a better measurement of amount in chemistry. What if we wanted to measure exactly how many molecules we have? Moles. Kind of. Moles. There we go. So we'll measure amount of gas in terms of moles. And lastly, we can also measure temperature of a gas. What would be a good unit for measuring temperature here? You might think Celsius, but remember, way back when in chapter 1, we talked about another SI unit of temperature that I said would become very useful later, Kelvin. This is where Kelvin comes into its own. We'll see a little later why you have to measure temperature of a gas in Kelvin. If you use Celsius, weird things happen. So we use Kelvin there. Now remember how we convert to Kelvin. We talked about that way back when. It's actually a pretty simple conversion factor. So if you have a Celsius measurement, just add 273.15 to it, and that will give you the temperature in Kelvin. So we can readily convert back and forth between those two. All right. Now one thing that I'm sure has been bothering all of you guys, and this is going to jog your memory here, everything about chapter 5 has so far been fairly math-free. I'm sure a lot of you have been disappointed by that. Let's see if we can get math back into the picture here. So we don't have to miss it after all. Okay. Well, if we want to do math with these measurements, we need some variables so we can do some algebra. What would be a good variable for pressure? P. There we go. So a nice capital P would be pressure. What would be a good variable for volume? V. Capital V. What would be a good variable for moles?
MOL.
MOL would sound tempting, but it's got 3 letters. That's way too many letters. So I shortened it down to E. E. I've heard a lot of weird answers for this, but never one that weird. Let's try something else here. What would be a single letter abbreviation for moles? M? Yeah, capital M's molarity.
What about lowercase m?
Lowercase m's meters. We're out of letters, aren't we? Let's just call it N. That sounds good.
That's out there.
We've run out of letters, we'll just call moles N and just be done with it.
That's E.
What would be a good variable for temperature? T. Capital T. Lowercase t would be time. So there we have it. We've got now variables that we can use to express these 4 measurements. And now what we're going to do is see how these 4 measurements interrelate when we're talking about gases. And your book actually goes through lots of exhaustive details showing how all these things interrelate to each other. What I want to show you right here today is you don't even need to read the book. You should anyway, but you don't need to. You already intuitively know all these relationships. Let's see how. First off, let's talk about pressure. Let's do that. Yeah, why not? Let's talk about pressure versus temperature. That'd be a good one. So, how do pressure and temperature of a gas relate to each other? Any of you folks in Boy Scouts, Girl Scouts, anything like that? You're a Boy Scouts?
I'm an Eagle Scout, yeah.
You're an Eagle Scout, wow. I didn't make it that far because I was kicked out of the Boy Scouts. We'll now discover why. So picture this. This was a nice, friendly Boy Scout camp out. We had a fire, roasted the marshmallows, told the ghost stories, all that stuff. It's about 2 in the morning, and everybody is asleep, except for Hawes. Hawes carefully sneaks out of his tent, goes over to the fire. And the fire is still burning. Not too hard, but it's burning a little bit here. There we go. Now, being a rather stinky 11-year-old, my mother sent a bottle or a can of Lysol with me. Lysol is pressurized with
Gas.
gas. Yes. Not only pressurized with gas, but pressurized with rather flammable gas, as it turns out. So what little 11-year-old Haas did, he took his can of Lysol, he stuck it into the fire. Uh-oh.
I thought you were just gonna spray it on, that would have been like,
That would have been lame.
yeah, that would
That's why you're an Eagle Scout and I was kicked out.
have created a bomb.
So what I did here is I stuck the Lysol can into the fire, into the hot coals, and then I went carefully and quietly back into my tent and just sat there and waited. Now, just intuitively, what do you think is going to happen as we heat up the contents of this can? What's going to happen as we increase the temperature? What's going to happen to the pressure in that can?
It's gonna increase.
The pressure is going to increase, yes. And what will happen first, I wouldn't recommend hanging out around to watch this, but what will happen first is the can will start to bulge a bit. And then, this is the real danger sign, you know that kind of dimple they have in the bottom of aerosol cans? That eventually pops out, like that. That's the point you want to run. Actually, a bit before that. Now, as the temperature increases here, the pressure is increasing, therefore the can is expanding here. Eventually the can can't handle this anymore and it ruptures. And now you have superheated flammable gas, and the liquid in there is ethanol, by the way. You now